Today, I'm going to talk about, in general, tool integration challenges in MBSE, and in particular, how these challenges revolving around interoperability and scalability can be addressed using the technologies that we develop. And some of these technologies actually are open source, so they can be tried and used even without any commercial engagement. And in fact, we are happy to support open source projects, not just the ones that we develop, but several others as well. So this is a part of the mission of this company. As I teased in the abstract of the presentation, I'm also going to include a case study related to this technology that we did earlier this year and last year with a company of Airbus, which is specifically a tool integration demonstration scenario. And last but not least, there will be hands-on demos today, because in fact, we are going to be revealing a live demonstration system that is publicly accessible on the internet for everyone to try, which is hooked up to the MMS installation of the OpenMBEE community, so that you can actually get your hands on quite easily this technology and try it for yourself, how it works for you. So to get started with the presentation, like I already introduced, we are dealing with problems and technologies that arise out of large-scale deployments of model-based systems engineering. I think the majority of you know very well what kind of challenges we are facing in this landscape. There is a number of tools that especially large organizations use. It's not very straightforward how to orchestrate them into actual processes involving multiple stakeholders that can sometimes span over several organizations. So IP protection and access control play a vital role here. And also everyone knows very well what kind of scalability challenges are observed in practice. For example, when you're working with large models and large repositories, where I'm talking about not just hundreds of thousands of elements, but millions or tens of millions. So for today's technology, this is something that is a significant challenge, not necessarily just from the technological point of view, but in many cases also from the organizational and maybe even cultural point of view. What works really well today, I think, or reasonably well, is obviously the traditional toolset, the desktop tools and repositories such as IncQuery Cloud, because they allow a systems engineer to work with standard-based languages in an efficient way with very convenient authoring features. And the frameworks themselves actually are extensible in the sense that, for example, custom plugins can be implemented for Magic Draw to ease some of the in-house specific processes. But when you go to the large and want to facilitate collaboration in the large with several teams, several stakeholders, and you want to try to automate some of these workflows with cloud-based deployments of these traditional tools, you face a lot of challenges, obviously. And this is exactly the scenario that we want to tackle with the tools and technologies and products that we develop. So we want to move or migrate large-scale change management and model checking, model validation, tool integration workflows, and many other things into the cloud to leverage the technological stack that is now common in cloud-based deployments, which are used by millions of users worldwide. And the ultimate goal, I think, of all this integration is essentially simplification. So what is today, a combination of several tools, some of them locally installed, some of them on some remote server, communicating through repositories and ad hoc integrations, it should be ultimately simplified down to the push of a button. Obviously, this is a very, very ambitious goal, so I'm not claiming that we are there and this is something that is trivial to solve, but I will try to show you today some of the things that we've been developing that can hopefully move in this direction. So this model checking tool suite, which we developed, is called the IncQuery suite of tools, which essentially are comprised of two main components, the IncQuery Server and the IncQuery Desktop, which we will see. The server can be deployed in the context of no magic tools, for example, accepting contents of your projects, models, and repositories stored in IncQuery Cloud or OpenMBEE MMS, as you will see today. And based on all this information that can be retrieved from this repository through the process called indexing, the server can facilitate all kinds of interesting user stories based on model queries, model transformations, and validation rules. The server itself is actually both kind of a framework and an end user product as well. So you can embed it into your own in-house toolchain as well as leverage the end user features. And it's not just any kind of query technology, but also one which has an enterprise-grade access control system built in, meaning that it enforces, for example, the access control policies that are defined within Teamwork Cloud, not allowing random users to issue queries over any kind of repositories, just ones that they are assigned to be using. Like I said before, the other component of this toolchain is called IncQuery Desktop, which is essentially a query authoring tool that is implemented as a commercial add-on for Magidraw and Cameo systems modeler, and you can actually use it to run queries and transformations for a purpose of reporting, validation, visualization locally. So this is something that you can install into your own local installation of Cameo. And in fact, the two technologies, so desktop and server, play together quite well. So, for example, the query definitions that you create using desktop can be embedded into a Magidraw project committed to a Teamwork Cloud repository. And then these definitions can be used by certain functionalities enabled on the server. So these two components of the toolchain are fully integrated. So I already mentioned a couple of times queries, model queries. What exactly I mean by such a query? Typically the ones that are complex, right? So not just simple things like, what is the attribute value of this particular value property and things like this, but also much more complex things that are necessary to define, for example, domain-specific validation rules. I think this particular example that I put here was inspired by a public presentation from colleagues from Boeing. So when I'm talking about complex queries, I'm talking about exactly these kinds of queries. So just to give you an idea of how this tool looks like I said, it's an add-on for Magidraw and Cameo that contributes some custom UI components to the user interface that allow you to define the queries and also run them locally and interact with them. And there is also a companion application, which is called the IncQuery editor, that allows you to work with the query definitions using a rather rich textual syntax, which supports not just syntax highlight, but also content assist in an interactive way. And by the language itself is also pretty powerful. I will get back to this very shortly. Its main functionality is to define run queries, but these queries can be integrated or hooked into various parts of the Magidraw framework. So, for example, you can very easily define active validation rules based on these query definitions, but also several other options exist. I will hint at this in a short while. What is IncQuery? IncQuery is a Viatra query language. It's an open source graph query language. It has been existing for a long time, actually more than 12 years now. And it's part of an open source project that is hosted at the Eclipse Foundation. It's essentially a model or graph query language that is specifically tailored towards meta-modeling scenarios. So where the graph or the model that we are querying has got a schema that is described by a meta-model that not only defines, structural consistency rules, but also, for example, a type system with full inheritance and so on and so forth. So in IncQuery, what you are writing are essentially patterns that can be interpreted or evaluated over an instance graph. And this pattern describes those conditions that instance graph has to fulfill in order to constitute for a matchable query. So for example, if you want to define a validation rule with this language that detects potential deadlock states, which are states that have incoming transitions but no outgoing ones in the simple case, what you would write in this language is essentially just three lines of code. It's a fully declarative language, meaning that you describe the end result of the query, not really how that should be computed. So I just highlighted on this slide how logically this language is used. You declare a pattern definition. You say that it's going to have one parameter, meaning that we are collecting those states essentially that are potential deadlock states. And we state that this should be a state that is not a final state. We also say that it has to have at least one inbound reference of type incoming and no outbound reference of type outgoing. So essentially the blue things such as state, state incoming, final state, state outgoing are meta types defined in the UML meta model. And everything which is in this weird purple color is a keyword of the language. And like I said on the previous slide, this companion application that is built into MagicDraw can help you a lot with using this language because it supports content assist, syntax highlight, and many other interesting features. If you want to know more about this language and about the underlying technology itself, like I said, it's all open source. So if you go to these URLs, which are on the bottom of my slides, then you can find a very nice tutorial that teaches you how to use this language. So once you have this language learned, you can use it for many other interesting things as well, using this desktop add-on, such as the definition of smart packages, custom tables, relation maps, and many other things, essentially because it's evaluated as a special kind of expression within MagicDraw. So wherever you can use expressions, you can use this language. The more interesting piece of this tool suite is called the IncQuery Server, which, like I said before, is essentially a server product that is hooked into the repository, like Teamwork Cloud or MMS. And in terms of the user interface, it's typically accessed by web-based applications. So this screenshot that you see here and that what you will see shortly in the demo is actually a browser-based application called the IncQuery Server Console, which gives access to essentially the majority of the functionality of the server, which is very similar to the desktop add-on, because it allows you to define queries, also with syntax highlight in this case, and also run these queries, or run the validation suites directly on the server, which are defined in terms of queries, and so on and so forth. The web-based application itself is subject to repository access control, like I stated previously. So if you deploy it with Teamwork Cloud, for example, then it requires you to log in through your Teamwork Cloud identity. In the MMS case, supported by a different authentication backend. Other than queries that you can run on an individual revision of a certain project or a model, the server, since it has access to the contents of the entire repository, it can do many other interesting things as well, such as repository-wide validation and change impact analysis. By change impact analysis, I mean the scenario where you want to investigate the cross-references between the projects that you have committed to the repository. For example, if you are making a change to a library project that is referenced by several client projects downstream, if I make a change to that library project, I want to know, how that change is going to affect these client or downstream projects. And the server can answer these questions very quickly by analyzing the contents of the entire repository. The unique aspect of this technology is a special evaluation engine, which is built on this Viatra framework that I mentioned previously. And this engine combines traditional persistence-based and also in-memory representations in order to reach a scalability that is much, much faster than what you would typically be able to achieve with traditional databases or even modern graph databases for that matter. So typically, a validation rule in the IncQuery server runs at least 10, sometimes even to 100 times faster than if you would implement the same in a Sparkle-based systems, for example. Like I said, not just the plain query functionality can be accessed through these web-based controls, but also, for example, the validation that is rendered like an interactive report. I will show you in more detail in the demo later. In terms of interoperability, we designed this system in a way that it's very easy to integrate with, meaning that all the functionality is exposed through OpenAPI, standard compliant endpoints that can be invoked directly from within the web console, but also using an interface called Swagger. And it's very easy to generate client code for these kinds of API definitions, for example, to languages like Python, which we will be using for the second part of the demo that features an integration with Jupyter. So Jupyter is a very nice tool. It's a kind of an interactive tool, largely based on Python, to create so-called notebooks that are, let's say, documentation pieces that contain embedded code segments that can be invoked and edited interactively. And I think Jupyter is a very powerful tool for reporting and model analysis scenarios. And we actually prepared today's demo in order to showcase some of the capabilities that can be implemented with the combination of Jupyter and IncQuery Server. So now just a few words about this case study in order to give you an idea of what this technology can actually be useful for in real world practice. Earlier this year and last year, we partnered up with a company of Airbus called A-Cubed in order to create a demonstrator for tool integration scenarios. Tool integration challenges at Airbus are very, very similar to what other large organizations who engage in MBSE are facing. They have many applications across several verticals. They have to serve a lot of different kind of users and stakeholders. And so this A-Cube division of Airbus has developed a conceptual framework called ADAM, short for Advanced Digital Design and Manufacturing. That is a platform that enables data continuity across all of these applications, addressing 5 layers, including data, modeling, semantics, model management, service integration, and also visualizations. So within this framework, we created a demonstrator for a tool integration scenario involving 3 different tools: Cameo for product modeling, MathWorks and MATLAB Simulink for trade-off analysis, and finally Microsoft Excel for report and dashboard management. And essentially, the idea of this demonstrator was to create a web-based system that enables the designer to interact with these tools through this automated framework, meaning that the modeler, for example, who works on systems model in the first place, should be able to access simulation and trade-off analysis powered by Simulink and reporting powered by Excel automatically without having to launch these tools manually, basically through the usage of a push-button solution. Another interesting aspect of this technology was that we evaluated also the scalability of the technology. So what happens if you're not working just with small models, but real large models, several millions of elements? How does this scale? And I can already tell you that it scaled quite well. Essentially, what we ended up creating was an automated system that facilitated the exchange of models through Teamwork Cloud as the repository, and all the tool integration, heavy lifting, so moving and converting the data using model transformations and facilitating or orchestrating the actual flow between the various backends was implemented as extension modules for the IncQuery Server. So in this particular case, IncQuery Server was deployed as a framework, essentially. And all the reports and the end results and essentially the interaction with this automated system was done using a web-based interface, allowing the designer to automatically access the generated Simulink model, for example, retrieve that and visualize it, and also do the same or pretty much the same with Excel. One thing that is maybe worth mentioning is that the actual orchestration itself was done by standard technology such as Jenkins, which is a commonly used server platform for build job or job scheduling and automation. So this is a very quick summary of this project. I talked in more detail about this at the No Magic Symposium earlier this year. I think the slides and the presentation is already online, so if anyone of you is interested to learn more about this, then check that out. I think Airbus also has a small website up giving some info on this project as well. Regarding our involvement in the OpenMBEE ecosystem, we've been working with tools and technologies coming out of this community for a long time now, actually several years, and we've tried to, let's say, contribute back as much as we could also in the past. So there's actually several frameworks available in our GitHub that can be interest to this community, like an integration with the Viatra framework for Magic Draw, and also an example project that illustrates how to do this in a custom plugin. We also created a fork of MDK that illustrates the uses of this technology, and there are several benchmarks and demos as well available for those of you who are interested in more in-depth details of the query and the transformation technology. This last link will be the one which is of the biggest interest for us today, because that's actually a special customized version of the TMT SysML model, the 30-meter telescope model, that we have been using for performance evaluations and also testing purposes. It was an extremely valuable asset. And also for today's demo, I think it will play a quite significant role, because I will be using that to showcase various capabilities of the technology. So now we are closing on what exactly is the thing that I'm going to show to you today. like I already hinted at, it's actually a live demo of the IncQuery server primarily that is available for everyone on this address, so openmbe.inquery.io. And like I said, it's actually hooked up into the openmbe.org installation of MMS. So it accesses the contents of the repository through the OpenAPI endpoint of MMS, and also exposes its own functionality through such an OpenAPI interface to the rest of the world. That OpenAPI will be used for Jupyter demonstration. The Jupyter notebook that I will be showing you today is actually deployable on a service called mybinder.org. That's a public service for hosting Jupyter notebooks. So for those of you who do not wish to install Jupyter locally on their own computers, it's a very convenient way to actually try the notebook yourself and play with it and see how that works. And what this demonstration system actually does is that it has access to all the public content of mms.openmbe.org and showcases some of the features of IncQuery Server, in particular custom queries and validation rules that can be also invoked through the OpenAPI endpoint. There is a possibility to give access to more. So for example, we've asked the operators of the system to allow us to see some of the organizations that are not public, such as the SysML submission team, SATRI, so that can also be accessed. But for us to be able to give to someone access to that, we need to contact us first, and we need to check that you actually have access to that in the first place. But I do encourage you to get in touch with us, because it's much more interesting if you have a more privileged user rather than just a public user. There is a landing page which I will be showing to you. There is the actual web console accessible through this system. And I will be also showing some of the interesting visualization and documentation capabilities of Jupyter. So with this, I'm going to go into another window. If you go to our website, IncQuery.io, there is a very easy shortcut to this live demo. So you just click on the launch demo link, and then it will take you to this landing page. And from this landing page, if you scroll down all the way to the bottom, this is the magic button that you will be looking for. And we also included the guest access, which is essentially identical to the guest access of MMS itself. So if you click on that button, something similar to this interface should come up. And this is essentially a simplified version of this IncQuery console. There is a tab for the Swagger UI. So essentially all the OpenAPI calls that are supported by this instance are exposed through this interface. I am not going to get into the details of each and every one of them now, because it will take too much time. But essentially, all of these API calls can be tried right within from this interface, and you can see what kind of result you get. Typically, it's all JSON serialization containing all the data and metadata that is relevant for a particular API call. Just to give you an idea of how this interface works, what you usually start with is the first tab called Index Manager, which shows you the contents of the repository, essentially. So these are basically the same things that you would be seeing if you log into MMS itself. These are the organizations which are on the top level of this structure. Under the organization, you have the project, then you have the branch, and then you have, in our case, always the last 3 commits. For our demo today, I will be using this special organization called IncQuery Server for MMS demos, which contain 2 models. One of them is called the validation UML example, which is just a small model. And the other one is the modified version of this 30-meter telescope model, which is a little bit larger. And if you want to run a complete validation, for example, on such a model revision, this is what you would typically do. So you would go to the validation tab, select the revision that you want to run the validation on, click on the element and select validate model compartment. So what do we see here? It's essentially a validation report that is very similar to the one that you would see in Cameo or Magitro, for example. So it's essentially a big table that shows you all the different validation entries that are computed from the model. So in this example, we have 4 rules, each of them defined in the VQual language. I will show this to you very shortly, how they look like. And these 4 rules are evaluated against the real TMT model, which is about 200,000-300,000 elements, if I remember correctly. And each row corresponds to a violation. So, for example, this is a state element that has a match on the deadlock states rule. That is actually an implementation of the example from the previous presentation with the message and the severity. And this is the overall distribution of this. This is actually an approximation of the deadlock state, meaning that that deadlock state is a state that has an incoming transition, but no outgoing transition, for example. So the system can potentially get stuck in that state during execution. This is the example that I was trying to explain in the PowerPoint presentation. So this is a static analysis. It doesn't execute the state machine, but it does check according to the structural properties of the model, whether you actually have a state that is a candidate for a deadlock because of the fact that there are no outgoing transitions from it. Back to the validation, and then I will come back to this interface. This is essentially, like I said, a big table that contains all of the entries that are computed from the model. Technically, it's actually a big JSON document that you can access here in this menu item. So this is how such a validation JSON document looks like. So it essentially contains a big array of all the different violations that are computed for a particular rule and element combination with links to the elements that play a role in that violation. You may have observed that these are actually hyperlinks here. So if I click on one of the hyperlinks, it will actually direct me to the REST OpenAPI endpoint of MMS itself, giving me a JSON serialization of the particular element that is of interest in that violation context. So this, as you can see, this is in fact an element which is an instance of a state. It has a name and also all the identifiers which allow me to actually identify this particular element either within MagiDraw or in View Editor and so on and so forth. So if you do a search on this ID in View Editor, it will give you which particular element we are talking about. This is a little bit technical, so it's not maybe the most useful for end users, but for people who are interested in using this technology as a framework, it's essentially all the information they need in order to be able to process this further. The ad hoc queries work in a very similar way. So I already showed you previously how this works. Here on the left, you don't see the models, but see the so-called query registry, which is essentially a hierarchical representation of all the queries that are known by the server. You can think of them as stored queries or registered queries analogously to database technology. And in fact, we've actually prepared this demo in a way that there are several examples already included. Like, for example, the circular activity call that finds circles in activity relationships. So, for example, this is again something that can be a potential problem if you have a circle in the invocation of your activities. And this plus operator you see here is a powerful feature of the Viqua language. It's called a transitive closure operator. So it computes reachability information or circles along the subgraph. And as you can see, it's all very quick. So I can actually show you the definition itself as it's seen in MagiDraw. This is how you see it through this MagiDraw add-on. What we are actually looking for in terms of transitive closure is this activity call pattern, which is essentially a call behavior, action dot behavior kind of relationship between a node and a call activity. So this is what, in this case, we are computing the transitive closure of, but this can be anything essentially. Okay, let's go back to the browser. So this is the ad hoc query interface. You can actually add queries yourself here if you are a privileged user. For the demo, I don't have that kind of access control, so I will be returning to this a bit later. And now maybe we should progress to the Jupyter part of the demonstration. Like I told you, we have created a Python binding for this OpenAPI that is actually released in an open source repository. So it's available on GitHub so that you can customize and tinker with it yourself. And basically, the simplest way of trying this demonstrator is to click on this Launch Binder button on the top of this README page. What this button will do is it will actually launch this Jupyter notebook on this My Binder service, which means that you will get an instance of Jupyter running this notebook definition that is tied to your browser. So as long as you keep that browser tab open, that Jupyter notebook will continue to run. And what I want to show you with this Jupyter demonstration is, for example, how this technology and the function of Jupyter can be used for the purpose of creating visual reports over systems engineering models. So essentially, the way Jupyter works is that you get an interactive rendering of your notebook document, which contains embedded code segments written in the Python language. And what this notebook does is essentially guides you to the process of connecting to the endpoint of the IncQuery server. Then it allows you to select in an interactive way which particular model revision you want to work with. So again, here you see all the things that my guest user can see from the system. I am going to pick this particular model. And then on this model, I can trigger the execution of the validation report, for example. So now exactly the same thing happens as what happened before, but now I get this validation report right within my document. So this table is now rendered using essentially Python objects that have been generated from the validation endpoint. And, this is still a rather technical thing. So maybe I want to create some visualization on top of this data structures. And this is where Python and Jupyter really shines. So for example, using a built-in plotting or visualization library, such as plot.ly, and I can create very easily things like this. So this particular plot shows the distribution of the validation results with respect to the various validation rules that I have run my models on. So deadlock states rule, send not receive signals, and so on and so forth. They each have different number of validations. This one, for example, has 15 instances in the TMT model. This one has 124. This one 153, and so on and so forth. Even more complex things can be done very easily using this technology. So for example, I can create a detailed diagnostic report which shows the number of violations per element. So it actually shows me those elements in my model in terms of IDs that have the biggest number of violations. In this case, it's rather low. So in this respect, we are still okay because it's actually just 2. But it's also color-coded with respect to the degree of the particular violation. Going further, obviously, not just simple things like validation plotting can be done using Jupyter, but also more complex things. So let's say that I want to create a coverage report, a requirement coverage report, which is essentially computation of, how the requirements captured in my SysML model relate to the blocks or actually the contents of the model. For example, what is the total number of blocks? What is the number of blocks that are strongly covered? And what is the number of blocks in a package that are weakly covered? By strong coverage, what I can do is I can write up a query using the Viatra language that essentially defines strong coverage as the disjunction of the existence of the satisfied by, verified by, and traced to relations between the requirement and the element. And by weak coverage, essentially what I can do is I can define it as a kind of a network sciencey property, meaning that I say that weakly covered elements are those elements that are somehow connected to strongly covered elements. And this propagation relationship, of which the transitive closure operation is again used for extending it to the computation of the entire graph, will be captured as the disjunction of property ownership or generalization. So this is, let's say, a custom query that my analyst has, let's say, written using the Viatra language. And once I have this done, I can actually proceed to run this query on the TMT model, make this transitive computation. As you can see, the results have been retrieved. So I already see some numerical values popping out for different packages. What I really want to show, for example, to my boss is a visual rendering of exactly the same kind of information. So I will go down a little bit further in order to create this coverage report, which is a detailed plot of this data showing how many non-covered blocks I have in my project and packages, how many weakly covered blocks, and how many strongly covered blocks I have. As you can see, it's pretty low. So actually, the requirement coverage report from the 30-meter telescope model is a little bit worrying because the overall coverage is quite low, especially compared to the total number of blocks. There are some further features further down this notebook. Since I'm a little bit short on time, I will just skip, but you are very welcome to take a look yourself and explore this demo. Like I said, it's all available as an open source component on GitHub, so you can take a look at the source yourself and also play around with the notebook. And now, just to finish up my presentation for today, I just wanted to give you a little bit of an insight as to where we are and what exactly we want to develop the technology towards. So as you could see, right now this demo is mostly focused on queries and validation rules specified using Viatra. One of the things that we've already done is to integrate also full text search and another language called Sparkle into this same system. You should see these features arriving in the public demonstration over the course of the summer. And later in the year, what we are going to release is an open API for integrating additional data sources to the system. So not just TeamWorks Cloud and MMS, but your own database or data management repository. And we also would like to work with the SysML submission team to implement a partial support for the upcoming SysML v2 standard so that the query server can actually be used to test some of the related functionality that is being worked in the SysML v2 submission team. And finally, our ultimate goal for this technology for early next year is to create a system that is capable of doing real federated search. So not just queries on one repository or one revision in a repository, but a combination of various data sources in order to empower, for example, reporting capabilities even further. In addition to that, finally, one of the most interesting aspects of the underlying technology is the capability to do not just batch queries like I showed you today, but also live or streaming queries that can process not just one static snapshot of a repository or a revision, but an evolving series of revisions. So series of commits, for example, that you do on a project, the system will be able to give you updates in terms of how that commit changed the result of a query or a result of a validation suite and so on and so forth. By federated search, I would mean that since we will provide an API for integrating these kinds of data sources, you will not only be able to index revisions from TeamWorks Cloud and MMS, but also from a GitHub repository, for example. And once this is done, then you will be able to issue queries like, what are the model elements that I have in TeamWorks Cloud and I also have in a model in a GitHub repository? Or what are the differences between these things, or how they are connected to each other, navigate along traceability relationship. Just to conclude, like I said, this system is now live and open for you to try. So I really encourage you to go there and take a look and try to push some of the buttons. And if you have any questions, then just feel free to get in touch with me at any time, and I will be really happy to answer any question you can have.